Now we're going to talk about another kind of series for which we can calculate the exact sum when it is convergent. So we've seen that this is the case for geometric series. Series with telescoping sums are essentially the other example where we can get the exact sum without too much machinery. So let's start with just an example. The series from 1 to infinity of 1 over n squared plus n. Well, we already have seen one analogy between series and integrals when we compared the series of 1 over n, the harmonic series, and the integral from 1 to infinity of 1 over x. And we use that to justify that the harmonic series of 1 over n, is divergent. So, as you may recall, we talked about integrating with partial fractions in order to integrate rational functions. Here we have a series where the general term is a rational function of n, so partial fraction may be useful. Let's see what we get if we try to get the decomposition into partial fractions of 1 over n squared plus n. And we factor the bottom, it's n times n plus 1, and that means that the decomposition into partial fraction is of the form a constant over n plus a constant over n plus 1. And in this case, the constants are easy to find. To find a, we multiply everything by n and set n equal to 0. In that case, we get 1 on the left-hand side and a on the right-hand side, so a is 1. To find b, we multiply everything by n plus 1 and set n equal negative 1. Then we get negative 1 on the left-hand side and b on the right-hand side, so b is negative 1. That means that 1 over n squared plus n can be rewritten as 1 over n minus 1 over n plus 1. Now that's interesting because if now we write out the partial sums for this series, when n is 1 we get 1 minus 1 half. When n is 2 we get 1 half minus 1 third. When n is 3, 1 third minus 1 fourth, and so on. So you see that negative 1 half in the first term is going to cancel out with positive 1 half in the second. Negative 1 third in the second term going to cancel out with positive 1 third in the third term, and so on. So each one of these terms are going to cancel out, except 1 at the beginning and negative 1 over n plus 1 at the end, because you see that each negative term is cancelled out with a positive term that comes afterwards. And so we end up with a simplified expression for the partial sum, which is 1 minus 1 over n plus 1. And now it's easy to figure out what the limit of the sequence of partial sum is, because if n goes to infinity, 1 over n plus 1 goes to 0, and therefore the limit of the sequence of partial sum is 1, but that means that the sum of the series is 1. So here we could not only show that it was convergent, that this series was convergent, but we could find its exact sum using this telescoping sum. I guess in this case it is quite obvious what we are referring to because all of the terms in the middle collapse in the partial sum. Let's look at another example that is a little bit complicated. The series from 2 to infinity of 1 over n squared minus 1. We start at 2 because the expression is not defined for n equal 1. So just like in the previous case, we're going to start with the idea that the decomposition into partial fraction of this rational function of n might be easier to handle. So 1 over n squared minus 1, the bottom factors as n minus 1 n plus 1, which means that the decomposition into partial fractions has the form a constant over n minus 1 plus a constant over n plus 1. And since we have only non-repeated linear factors, we can use the n-cover method. And therefore, it's easy to find a and b. To find a, we multiply everything by n minus 1, set n equal 1, and we get 1 half on the left-hand side and just a on the right-hand side. And for b, we multiply everything by n plus 1, set n equal negative 1. And we get negative 1/2 on the left-hand side and b on the right-hand side. Therefore, the decomposition can be written as 1/2 multiplied by 1 over n minus 1 minus 1 over n plus 1. So again, we write what that means for the partial sums. So we have 1/2, and then when n is 2, we get 1 minus 1/3. When n is 3, we get 1/2 minus 1/4. When n is 4, we get 1/3 minus 1/5, and so on. And then I have written out the last three terms, so for n minus 2, n minus 1, and n. So now we see that some things cancel out. So we have some telescoping effect again. 1 doesn't seem to cancel out with anything. Negative 1/3 cancels out with a positive 1/3 that comes 3 numbers later. 1/2 here doesn't seem to cancel with anything because the negative terms now are negative 1/4, negative 1/5, negative 1/6, and so on. So 1/2 is going to stay there. And then positive 1/3 was already cancelled with negative 1/3. So we have these two terms in blue, 1 and 1/2, that do not cancel with anything. Negative 1/3 is cancelled with something further down, so is negative 1/4, which cancels out with positive 1/4. And then negative 1/5 is going to cancel out with a positive 1/5 that comes later, and so on. Okay, so everything is going to cancel out, and let's see what happens at the end with the last few terms. Positive 1 over n minus 3 cancels out with something that comes before, because you see that each time we get first the negative term, like negative 1/3, and then it cancels out with a positive 1/3 that comes later on. So here we have a negative 1 over n minus 3 that is a few terms down, and that cancels out with this positive 1 over n minus 3. So this is going to cancel out. Then we have this negative 1 over n minus 1 that cancels out with 1 over n minus 1 that comes a few terms down. 1 over n minus 2 on the other end also cancels out with some terms that come before, right? Just like 1 over n minus 3, some term that comes here. However, this negative 1 over n would cancel with a term that is coming after we stop. So essentially, that means that this term is going to stay there, doesn't cancel with something that comes later on. 1 over n minus 1 cancel, as we have seen, cancels a negative 1 over n minus 1 that comes before, and this term would also have to be cancelled with the terms that comes later, so it's going to just stay. And that means that a simplified expression for our partial sum is 1/2 of 1 plus 1/2. These are the two terms at the beginning that do not cancel out. And then we have two terms at the end that do not cancel out, which are negative 1 over n and negative 1 over n plus 1. So with this expression, we can easily calculate the limit of Sn by letting n go to infinity. Then 1 over n goes to 0, 1 over n plus 1 goes to 0, and therefore the parenthesis goes to 1 plus 1/2, which is 3/2. When we multiply by 1/2, we get 3/4. So the limit of the sequence of partial sum is 3/4, and that is the sum of our series. So we have again an exact sum for this convergent series. Let's take a look at one more example where we do not really have a rational function like in the previous cases, but we have a similar telescoping effect. Namely, the natural log of n over n plus 1 can be rewritten because of the logarithmic laws, natural log of n minus natural log of n plus 1. Which means that if we write out the nth partial sum, we have ln of 1 minus ln of 2, plus ln of 2 minus ln of 3, then we have plus ln of 3 minus ln of 4, and so on. And we finish with ln of n minus ln of n plus 1. So we have ln of 1, which is 0, then two consecutive terms that cancel, two consecutive terms that cancel, and then this ln of n minus 1 cancels with the previous term, negative ln of n plus ln of n cancel out. So everything cancels out except for ln of 1, which is 0, and negative ln of n plus 1, the last term. So that means that the partial sum Sn simplifies as simply negative ln of n plus 1. But as n goes to infinity, ln of n plus 1 goes to infinity, and therefore the limit of the sequence of partial sum is negative infinity, which means that our series is divergent. Now, we have found that we can find the exact sum in two cases. For geometric series, where the common ratio has absolute value less than 1, or for series where we can calculate the sum using telescoping sums for the partial sums. Now, a natural result that is really just a rephrasing of what we have seen for sequences is a general result on operations on convergent series. So if we have the series of AN and the series of BN that are two convergent series, here it's important that they are convergent, and we take C a constant, then when I build a new series by taking the sum from 1 to infinity of this constant C times AN, it's again a convergent series. And similarly, if I add the terms in both series, the terms of corresponding index, I can build a new series, a series of AN plus BN. And similarly, if I subtract the terms of corresponding index, I can get the series of AN minus BN. All these series are convergent, and to obtain the sum of the series of general terms C times AN, we multiply C by the series of AN. Similarly, the sum of the series of AN plus BN is simply the sum of the sums of the two series of AN and series of BN. And the sum of AN minus BN is the sum of the ANs minus the sum of the BNs. All this is very natural, and it is easily proved if you write out what it is that we are stating. So let me just explain a little bit what's going on with this particular one. A series of a sum is the sum of the series, assuming that all the series are convergent. We have if we write out the partial sum for the series of AN, so we have A1 plus A2 and so on up to AN, and the partial sum for the series of BN, B1 plus B2 and so on plus BN. And we add these two partial sums for the same index, so we have n terms in each one of these partial sums. We add them together, and we can add term by term. We have A1 plus B1 plus A2 plus B2 plus A3 plus B3 and so on up to AN plus BN. And so what we obtain is the partial sum for the new series of general term AN plus BN. But now we have seen that if we have two convergent sequences, then the limit of the new sequence formed by adding the terms of corresponding index is the sum of the limits. This is something that we have seen on sequences. So here the limit of the partial sums for the new series is the sum of the limits of the partial sum. So by definition, now note that in these previous results on the series of a sum, series of a difference, of a constant multiple, we didn't have any corresponding results for product or quotient. This is another analogy with integrals, right? The integral of a sum is the sum of the integrals. The integral of a constant multiple is a constant multiple of the integral, but the integral of a product is not the product of the integrals, and this is why we have to develop all these integration techniques to deal with products and quotients. This is a little bit similar with series. Now, illustrating the result we had before, let's say we want to calculate the sum of the series from n equal 1 to infinity of 3 over n squared plus n plus 1 over 3 to the n. We have seen, using this telescoping sum, that the series of 1 over n squared plus n is convergent and is equal to 1. And on the other end, the series from 1 to infinity of 1 over 3 to the n is really a geometric sum, a geometric series of common ratio 1/3 and first term 1/3. So it is convergent because 1/3 is in absolute value less than 1, and the sum is a first term 1/3 divided by 1 minus a common ratio, which is 1/3. So we end up with 1/3 divided by 2/3, which is 1/2. But now we know that these two series are both convergent. So the series of 3 over n squared plus n is going to be 3 times the sum of the series of 1 over n squared plus n, so that's going to be 3. And our series is really 3 times the series of 1 over n squared plus n plus the series of 1 over 3 to the n, so that is 3 plus 1/2, 7/2. So now it is time for you to do some homework on series.